We continue with the section 4.3 notes. We're currently in example 2, find the exact value of the logarithm using logarithm rules and properties. And we're ready for part B to evaluate log base 4 of 16 times the cube root of 4. Again, we're just trying to obtain some experience and practice using the various rules and properties of logarithms. There are quite a few different properties that are in play many times, and you want to get comfortable using them. And hopefully these examples will facilitate that. So let's look at this one. Notice we have a product. By the product rule for logarithms, we should be able to write this as log base 4 of 16 plus log base 4 of the cube root of 4. So the logarithm of a product becomes a sum of logarithms. Now, let me just rewrite the first logarithm. The second logarithm can be expressed as, one moment, I went back and erased something. I want to go ahead and rewrite both of these logarithms in the same step. Log base 4 of 16 I'm going to write as log base 4 of 4 to the second. And the cube root of 4 can also be expressed in terms of an exponent. That would be 4 to the 1/3 power. Remember, the nth root of a number is the number to the 1 over n power. And then, as you recall, we at the end of the previous video wrote log base a of a to the x equals x, the cancellation property of logarithms. So we can apply that here. The first logarithm would have to just be 2. The second one would have to be equal to 1/3. And then we can combine those together. We could just write 2 and 1/3. Or if you want to write it as a common fraction, as 7/3. In example 3, we'll continue to apply the rules and properties of exponents to expand and simplify logarithmic expressions. In this case, we have some variables involved. So expand the logarithm as much as possible and simplify. Log base 2 of 8xy squared. Notice 8xy squared is a product, so the product rule should apply. We should write this as log base 2 of 8 plus log base 2 of x plus log base 2 of y. Now we can do a little bit of rewriting. 8 is a power of 2, so that's log base 2 of 2 cubed. And then the next two logarithms, oh, I'm sorry, I left off the exponents. Should be y squared there, excuse me. Log base 2, okay, what I meant to say, log base 2 of x cannot be really simplified any further. The third logarithm, what we could do is at least bring the exponent to the front. That's the power rule of logarithms. You can bring exponents down and treat it as a multiplication. And then another thing we could do is use the cancellation property of logarithms, or the inverse property. Log base 2 of 2 to the third is just going to simplify to 3. And then the other two logarithmic expressions just should be recopied as they are. There's nothing further we can do with them. And that completes the rewriting of the logarithm in part A. For part B, notice we have a square root. A square root is a power. This is a natural log. And that would be x minus 1 over e to the third to the 1/2 power. The power can then be brought to the front of the logarithm by the power rule. Then we have the logarithm of a quotient by the quotient rule. That can be written as a difference of logarithms, ln of x minus 1 minus ln of e to the third. And then there's one additional property of, with natural logarithms, ln and e are essentially inverses of each other. So we have this cancellation rule, ln of e to the x equals x. So for the last expression, ln of e cubed, that should simplify just to the exponent of 3. The other thing I should mention is this first expression, ln of x minus 1, cannot be expanded as ln of x minus ln of 1. We cannot split up the logarithm of a sum or difference. So you want to avoid rewriting such logarithms. So let's write this as, I will distribute the 1/2 at least. 1/2 of ln x minus 1 minus 1/2, and then ln of e cubed is going to be 3. And then the last expression can be written as, so we have 1/2 ln x minus 1 minus 3/2. And that would be far enough in terms of expanding the logarithm and simplifying it. Moving on to example 4, we can use our properties in reverse and take an expression consisting of sums and differences of multiple logarithms and write it as a single logarithm, assuming all of the logarithms have the same base. So let's look at part A. Log of x plus log of x plus 1 minus 2 log of y. All of these are base 10 logarithms, so this can actually be combined as a single logarithm. What we can do with the first pair of logarithms, since it's a sum, that can be written as the logarithm of a product, x times x plus 1. I'll write it like that. The second logarithm, we can get the 2 out of the way by writing it as an exponent. That's applying the power rule for logarithms. So now we have 2 logarithms. We don't have anything in front of the logarithms. We have a difference, and recall that differences of logarithms are associated with logarithms of quotients. So this could then be written as log of x times x plus 1 over y squared. Notice it's a single logarithm. It's not log over log. It's a single logarithm of x times x plus 1 over y squared. Now you could multiply out x times x plus 1 if you wished, but that's not absolutely necessary. It's sufficient just to write it in this form. It is indeed a single logarithm, and it can't really be simplified any further than it is. In our second example, we have natural logarithms. Everything's natural log, so again, all of these logarithms have the same base. The base is e. There's a couple of ways we could proceed in simplifying this or writing it as a single logarithm. Let me just take one approach. Maybe it's not the best one, but it will work. If we focus on the difference of logarithms in the parentheses first, I'll just leave the 4 there. Remember, by the quotient rule, that can be written as single logarithm of the quotient of b over c. Then by the power rule, the 4 can be brought up as an exponent and brought from being in front of the logarithm. So now we could write ln A minus ln B over C to the fourth power. And then we could, again apply the quotient rule. So we're going to do it a second time. ln of A over B over C to the fourth. Okay, now we don't want to leave it like this because it's sort of a complex fraction. So remember that when you divide by a fraction, it's the same as multiplying by the reciprocal. So let's write this in a little bit nicer form. ln of, think of that as A times C over B to the fourth, taking the reciprocal and multiplying. And then that could be written as ln of A times C to the fourth over B to the fourth. That whole expression is contained within the natural logarithm. This is one approach that you could use for writing this expression as a single logarithm. It's not the only approach that we could take. For example, you could distribute the -4 through the parentheses and then approach it that way, and you might actually find that to be a little bit easier than the method I showed you here, but it will end up giving you the same result in any event. To conclude this section, a logarithm may be evaluated by expressing it in terms of either common logs or natural logs using one of the following equivalent formulas. These are the so-called change of base formulas. And what these allow us to do is to evaluate logarithms with bases that are something, say, other than base 10 or base e, which are the logarithms that we can evaluate directly on a calculator, using by expressing in terms of base 10 or natural logarithms. So there are two versions of this, and you can use either version. Log base a of x equals log of x over log of a if you want to use base 10. Or if you want to use natural logs, which is what I usually do, log base a of x is equal to ln of x over ln of a. So ln of x divided by ln of whatever the base happens to be. Again, you can use natural logs or base 10. For example, log base 3 of 0.2 could be expressed as ln of 0.2 over ln of 3. And then we can use a calculator using our ln key to approximate this to however many decimal places we wish. To 3 decimal places, it's negative 1.465. That's using natural logarithms. If I replace ln with log, log, it works exactly the same way. I just prefer to write it using natural logs. I have to write one fewer letter that way, and that always appeals to me, to do it the simplest way I can. As a second example, log base 1.08 of 2. This was a logarithm I introduced at the beginning of the section 4.3 notes to introduce the idea of a logarithm as being an exponent. It was the amount of time it would take to double the size of an investment at 8% interest compounded annually, if I recall. I hope I have that right. But using natural logs and the change of base formula, this can be rewritten as ln of 2 over ln of 1.08. And then we can use a calculator, just enter it the way it's written there to approximate this. 9.006 is what we obtain, and if you look back in the notes, you'll see that we said that that logarithm had a value of approximately 9, so it agrees with that. So that's the change of base formula using natural logs or base 10 logs. The choice is up to you. That concludes the section 4.3 notes.